Hi, hello, welcome. This is Discrete Mathematics, and today we are talking about section 1.3, Conditional Propositions and Logical Equivalences. First up today, we'll look at what is a conditional proposition. A conditional proposition is a classic if-then statement. If it is raining, then the sidewalk is wet. Here we can let proposition P be it is raining, and then Q would be the sidewalk is wet. If P then Q, we use the symbol P and then an arrow Q. This is read implies. So this would be read P implies Q. Over here on the right, we have our truth table. Here we have all the possible combinations of P and Q. True, 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 false, false, true, and false, false. And we have our values, our truth values for this conditional proposition. P implies Q. If P is true and Q is also true, then we have a true statement. If P is true and Q is false, if it is raining and the sidewalk is not wet, that is false. If P is false, then it doesn't really matter what Q is because our original statement is false. So we have true values here as well. So the only way P implies Q is false is when P is true and Q is false. We have another example down here. If you become my friend, so this is P, then, I don't see the word then written, but it's right there, then I will give you candy. This is P implies Q, where P is become my friend and Q is I will give you candy. Here we want to write another truth table for three different propositions, P, Q, and R. And here we have all the different possible combinations. When you write these truth tables, these left-hand columns will be preset. If you are writing the table yourself, you would write this part, but you're not changing any of these values. All these values are the set values. So the statement that we're interested in is P or Q, this is our or from last time, implies not R. So that not is also a symbol from last time. So we'll work through all of these values. Let's see, P or Q. If P and Q are both true, then this is true. True implies not R, which would be false. So this is false. Next up, P or Q, true or true is true, implies not false, which is true. True implies true, that's true. P or Q, true or false is true, implies the opposite of true, which is false. This again is false. True or false is true, implies, let's see, the opposite of false is true. That one's true. False or true is true, implies the opposite of true, which is false. This one is false. Here I have false or true, which is true, implies true. That one's true. False or false is false. And it doesn't really matter what is over here because this will be true. And then this one also doesn't matter and it's true. So here is our truth table for this complicated proposition. Let's look at some more ideas. If P then Q, we can say that P is a sufficient condition for Q when the occurrence of P is all that is needed for the occurrence of Q. So an example would be something like being a dog is sufficient for being an animal. All dogs are animals. So if you're a dog, then you're an animal. It's like it's enough. A synonym for sufficient would maybe be enough. Q is a necessary condition for P, which means that P cannot occur without the occurrence of Q. So an example for this one would be something like being a dog is not necessary for being an animal. There are other ways to be animals than being a dog. So being a dog is not a necessary condition, but I could look at it the other way. Being an animal is necessary for being a dog. All dogs are animals. There's no dog that's not an animal. So if you are an animal, then you could be a dog also. So this is a required condition. You are required to be an animal if you're a dog. Let's look at example 1. Write each proposition in conditional propositional form. So we're going to use words here, not symbols. Betty will be a good student if she studies hard. Here is the if portion. So if she, which is Betty, studies hard, comma, then she will be a good student. If then. Next one, when you sing, my heart will be warmed. A synonym for when is if. If you sing, comma, then my heart will be warmed. That's my heart symbol there. If you sing, then my heart will be warmed. A necessary condition for you getting a good grade is that you read every section that we cover. So up here we said that P, we're doing necessary. Q is a necessary condition. So the necessary condition here is that you read every section we cover. So this is Q, and then getting a good grade is P. So if we rewrite this one, if you get a good grade, then you read every section we cover. Our textbook is actually quite readable, and I recommend that if you want to get a good grade, then you read every section we cover. Next one is about sufficient. A sufficient condition for being in a math class is taking calculus. So taking calculus here is our P, because P is a sufficient condition. And then Q is being in a math class. So if you are taking calculus, then you are in a math class. That is enough to be in a math class, is if you're in calculus. There are other ways to get a good grade in this class, but one of the ways is you have to read every section. That is a necessary way. But it maybe isn't the only thing you have to do. You might also have to do other things, but it is one of the required things. So that's necessary versus sufficient. We are ready to move on to different types of statements. In these different types of statements, we're going to look first at the converse. So our conditional proposition is that if it is raining, then the sidewalk is wet. P implies Q. The converse is Q implies P, the exact opposite. If the sidewalk is wet, then it is raining. And we can think about, if P implies Q is true, is it always true? Is the converse always true? If when it's raining, the sidewalk gets wet, would it be true to say if the sidewalk is wet, then it is raining? Or are there other ways for the sidewalk to get wet that don't involve raining? Like someone spilling their coffee, or maybe someone dumping a bucket of water. So is the converse always true? Not necessarily. The converse being true does not follow from P implies Q being true. Next up is inverse. If we look at the conditional proposition P implies Q, its inverse is not P implies not Q. So same order, but we're adding in the double nots. So here I have the inverse is, if it is not raining, then the sidewalk is not wet. And I can think about, is this statement have to be true if P implies Q is true? If it's not raining, then the sidewalk is not wet. Well, it could be true that it is not raining, but the sidewalk is still wet. But is it possible? So that would mean that this one is not true either, kind of for the same reasons as above. Someone spilled their coffee, someone dumped a bucket of water. The sidewalk could be wet even though it's not raining. So this is also not always true if P implies Q is true. The next one that we're going to look at is called the contrapositive. So we have P implies Q. The contrapositive would be not Q implies not P. So it's like it's the inverse of the converse. It's like these two combined together. The order is opposite and we have the nots. The contrapositive statement is, if the sidewalk is not wet, then it is not raining. So if the sidewalk is not wet, that means the sidewalk is dry, it's not raining. And is that always true? Yes, if P implies Q is true, then the contrapositive is always true. The sidewalk is dry, that means it's not raining. It can't be raining and the sidewalk be dry. That can't happen. Okay, another type of proposition are called bidirectional propositions. If P and Q are propositions, then the proposition P if and only if Q is called bidirectional. And here we see bidirectional meaning two. So the arrow implies goes both ways. So P if and only if Q. If and only if is kind of allowed to write. So we often abbreviate that if spelled with two F's. So we like take this and then we take like this very last F and we kind of ignore this middle part. If and only if. P if and only if Q. That's P implies Q and Q also implies P. Bidirection, it goes both ways. Let's take a look at our truth table. We have all possible combinations of P and Q. So P if and only if Q. If both of them are true, then the statement is true. If true implies false, we know that one's false from before. This one is also false because we're looking, if we do Q implies P, then we would have true implies false, which is false. So here's this one's false. And if they're both false, then this is true. So here we have the false values coming in when P and Q are different. So you can go back and compare this truth table with the one-sided, and the difference that you're going to see is here in this third row. Is the statement 2 is less than 3 if and only if 4 equals 8 minus 4 true or false? Well, let's evaluate the truth value of 2 is less than 3. That's true. Let's evaluate the truth value of 4 equals 8 minus 4. That's also true. So we're looking at true if and only if true. And if we look back at our truth table, we see that this is true. Okay, we are ready for example 2. I want to formulate each symbolic expression in words, and I want to also do the opposite, write each statement as a symbolic expression. So we're kind of doing both in this one example. In this one, P is today is Monday, Q is it is raining, and R is it is hot. First up, I have not P implies R and P. Or sorry, not Q implies R and P. This is an and. So I'm going to start off with this is an if, and then this here thing is my then. So if not Q, it is not raining. Then and it is hot and it is today's Monday. Then it is hot and today is Monday. For me, at the time of this recording, today is actually Thursday, but we're going to set that aside. This is how I would write this statement in words. In part B, I want to take a look at writing this statement with symbols. Today is not Monday. Let's see, not Monday is not P. If, here's my if. It is raining and it is hot. Okay, so let me think about this. It is raining, that's Q, and it is hot, that's R. But this is where the if is, so it's all of this implies today is not Monday, which is not P. So I'm going to rewrite this as Q and R implies not P. If it is raining and it is hot, then it is not Monday. Last one for this one. It is not the case that today's Monday. Today's Monday is P. Or it is raining, Q, if and only if it is hot, R. So let's see. It is not the case that today is Monday or it is raining. So I'm going to do not the case that P or Q. If and only if it is hot, R. There is this one using symbols. Ready to move along to example 3. Write the conditional proposition symbolically. Write the converse and the contrapositive symbolically and in words, and then I also want to find the truth value of each proposition. Absolute value of 1 is less than 3 if -3 is less than 1 is less than 3. I'm going to rewrite this using my classic if-then structure. If -3 is less than 1 is less than 3, whoopsie, that's like too many bumps in my 3, then the absolute value of 1 is less than 3. So this is if Q, then P. So I'm going to let P be absolute value of 1 is less than 3, and Q be -3 is less than 1 is less than 3. It doesn't really matter what you label things as long as you write down what you're labeling them, and then you use them correctly in the way that you write them. So I'm looking at some truth values here. Absolute value of 1 is less than 3, that's true, and -3 less than 1 less than 3, that's also true. So both of these are true. So write the conditional proposition symbolically. That is Q implies P, which is true implies true, and that is true. So we'll maybe say that that was A. Next up, I want to write the converse. I'll do that in B. So my converse is going to be the opposite of this. P implies Q, which is true implies true, which is still true. And I want to write that one in words. If the absolute value of 1 is less than 3, then -1 is less than 3 is less than 1. And last up, contrapositive, symbolically and in words. The contrapositive of Q implies P is not P implies not Q. And that is false, implies false, which is true. To write this one in words, I want if not P. So if the absolute value of 1 is greater than or equal to 3, then the opposite of Q. The opposite of Q is going to be the opposite of this. So this is 1 is between -3 and +3, so I want the opposite of that. So that's going to be -3 is greater than or equal to 1, or 1 is greater than or equal to 3. All right, equivalent logical propositions. If two propositions have the same truth values in a truth table, then the statements are considered equivalent. And we're going to use the symbol 3 equal signs, means equivalent, whereas 2 equal signs means equal. So in programming, to show two statements are equivalent, you would use a double equal sign, usually in most languages. Suppose that P and Q are logical propositions and they have the same truth tables, then we can say they are equivalent. P is equivalent to Q. Triple equals, three bars. Notice that the truth of a proposition does not necessitate the truth of its converse. So we talked about that already. If a proposition is true, its converse isn't automatically true. But a proposition and its contrapositive are equivalent. So if a proposition is true, then its contrapositive is also true. And here's how we would write that. P implies Q is equivalent to not Q implies not P. So we're going to take a look at truth values here in our truth table. We're going to show this relationship. So P implies Q. Our truth table for that is true, false, true, true. We've done this one before. Let's take a look at Q implies P. True implies true. That is true. False implies true. That is also true. True implies false. That's false. False implies false. That's false. So here we see this one right here is the converse. And the converse has a different truth table than the original proposition. Sometimes it's the same. And so that's why I said it doesn't necessitate. Sometimes they might both be true, but it's possible that one of them's true and one of them's false. Next up, we have not P implies not Q. This is the inverse. So let's see, not P is false implies false. That's true. False implies true. That's also true. True implies false. That's the one that's false. And true implies true. That one's also true. One thing I'm noticing is that this one and this one are the same. Oh, they should be the same. This should be true. Did I say true and read the wrong thing? Hopefully. These two are actually the same. And actually the inverse is the contrapositive of the converse. Inverse is contrapositive of the converse. So therefore, Q implies P is equivalent to not P implies not Q. That's kind of cool. The last one we want to look at, this is the converse of our original statement, P implies Q. Or not the converse, this is the contrapositive of the original statement. And let's take a look at its truth values. Not Q implies not P. So false implies false, that's true. True implies false, well, that's false. False implies true, that's true. And true implies true is also true. So now I'm seeing that these and these are the same. Come over here. These are also the same. So therefore, P implies Q is equivalent to not Q implies not P. So here we've established that a logical proposition and its converse are equivalent, and its contrapositive are equivalent. And we've also established that the inverse is the contrapositive of the converse. And so those two are also equivalent statements. All right, we're ready to use our truth tables to show De Morgan's laws for logic. So let's just do a little review here of De Morgan's law for sets. De Morgan's laws for sets say that A union B, the complement of that is the complement of A intersect the complement of B. So here we have the version of that for logical statements. Not P or Q is equivalent to not P and not Q. So when you can think of it as distribute that not, we have not P and not Q. And then the or changes to an and we see something similar happening over here. And then we also have the one where the or and the and are switched. So let's take a look at these truth tables. This showing a truth table is a way to prove whether two propositions are equivalent to each other. So I have not P or Q. Let's see, P or Q. They're both true. I have not true, which is false. Here I have not true, which is false. Here I have not true, which is false. And here I have not false, which is true. So that is this side of this first De Morgan's law. Now we're looking at this side over here. That one's right here. I have false and false, which is false. I have false and true, which is false. I have true and false, which is false. And I have true and true, which is true. So now I'm seeing these are the same, which means these two statements are equivalent. So we have proved that first one. Let's look at proving the second one. Not P and Q is equivalent to not P or not Q. So here I've got not P and Q, which is true, and that's false. I have not P and Q, which is false, which is true. I have not false, which is true. And I have not false, which is true. And that was this one right here. Let's look at this one over here. Not P is false or false, which is false. I have false or true, which is true. I have true or doesn't really matter. In this case, it's false, which is true. And I have true or true, which is true. So here I have these are the same values in my truth table. So these ones are equivalent as well. So we've now shown that second line is true. Not the quantity P and Q is equivalent to not P or not Q. That is De Morgan's laws for logic. We are moving on to example 5. This is the last one in this section. I'm going to let P be P or the quantity Q or R, and Q be P or Q and Q or R. Is P equivalent to Q? So in order to answer this question, I need to make a truth table. And I need to include P, Q, and R. And here I get to make my own truth table. So here's P, Q, and R. And I'm going to do all the combinations of P, Q, and R. So true, true, and true. There's actually going to be 4 trues and 4 falses. And then 2 trues, 2 falses, 2 trues, and 2 falses. There are multiple ways to set this up, but this is the way that I like to do to help me make sure I get every combination. It's 4 trues, and then 2 trues, and then 1 true. So I'm going to have my statements over here, my propositions, P and Q or R. And then I'm going to look at P or Q and P or R. And now I'm ready to fill out my table, and if it's exactly the same, they're equivalent. If even one row is different, then they are not equivalent. Okay, here we go. P, which is true, and Q or R, which is also true. So true. P, which is true, and Q or R, which is true, is true. P, which is true, and false or true, which is true. P and false or false, which is false. So this one is false. And here I have false and again, it doesn't really matter what this is. False and is going to be false because in an and situation, both things have to be true. So here, when all of these P's are false, these are all going to be false. So I save myself a little bit of time there. Let's look at the next one. P or Q is true, and P or R is also true. True, true. So far we're looking good. I'm looking at this true compared with that true. So far, thumbs up. P or Q is true, and P or R is true. Next one, P or Q is true, and P or R is true. Next one, P or Q is true, and P or R is true. Oh, here I'm seeing this one was false, this one is true. So I wouldn't really need to continue because I already found one row that's different. I think I will continue just so we can get the practice, but this is where I could stop and I could say they're not equivalent, but I'll just keep going because I might as well finish it off. Let's see, P or Q is true and true, which is true. So again, another row that's different. P or Q is true and false. Oh, this one's false. And this one's false. So this is going to be false, false, and it doesn't matter. And then this is another false and. So here I actually had two rows that were different. So since these are not the same, that implies that P is not equivalent to Q. And I've showed that with this truth table. And that is it for this section. I will see y'all next time.